This is section 8.4, part 2. Okay, we were about to do example 2, part D. All right, so let's look at this one, part D. This is the integral of the square root of x squared minus 2x dx. So this doesn't quite look like what we're used to seeing in these problems because we're expecting a function of x squared plus or minus a number. So what we're going to need to do here, we'll go off to the side and do a lemma, is I'm going to need to complete the square. So to complete the square, since the coefficient of x squared is already 1, I need to add half of the coefficient of x is -1. The square of -1 is 1, so I need to add 1. But if I just add 1, I've changed the problem. So what I can do instead is add 0 in the form of 1 minus 1. This part factors to be x minus 1 squared minus that 1. And so we can replace the radicand with x minus 1 quantity squared minus 1. And now that's in the form of u squared minus a squared. So our u squared, which is x minus 1 quantity squared, means that u is equal to x minus 1. Our a squared is 1, which means a is 1. And if you'll recall, the u squared minus a squared uses the substitution a, which in this case is 1, secant of theta. So if I take the derivative on both sides, the derivative of x minus 1 is 1 times dx, and the derivative of secant theta is secant theta tangent theta d theta. Okay, so we're ready to substitute. This will be, forgot to draw the integral sign, sorry about that. The integral of the square root of, since x minus 1 is secant of theta, the square of x minus 1 will be the square of secant, so secant squared theta minus 1, and then dx is replaced by secant theta tangent theta d theta. Kind of running into my lemma over here, so let me move that out of the way. All right, and then of course secant squared theta minus 1 is tangent squared theta times secant theta tangent theta d theta, and the square root of tangent squared theta is tangent of theta multiplied by the other tangent theta makes this secant theta tangent squared theta d theta. All right, so now what? Well, what we're supposed to do in this kind of situation is to replace the secant theta, replace the tangent squared theta with secant squared theta minus 1, which is the integral of secant cubed theta minus secant of theta d theta. All right, and so splitting that into two integrals, we're going to have the integral of secant cubed theta d theta. Let me go back and make sure this looks like a parenthesis on the left side there. Minus the integral of secant of theta d theta. Well, we have a formula for the integral of secant of theta d theta, so I'll come back to that one in a little bit. But the secant cubed, let's go to a lemma. Well, that means this one up here is lemma number 1. For this problem, I'm going to actually need more than one lemma, so that's lemma 1. And this is going down here is going to be lemma 2. Make sure I leave enough room up there for what we're going to need to do at the end of the problem. What is the integral of secant cubed theta d theta? Okay. So back when we were dealing with the product of secants and tangents, this one, an odd power of secant alone, no tangent of theta in there, the hint was that we would do this by parts. And so I'm going to split this into two parts. Here, paying attention to detail doesn't help much because it's all secant of theta. The only thing is that we need to assign to u and dv the correct thing so that we can get a good answer. And if you'll recall, the derivative of tangent is secant squared, which means I really want to make my dv secant squared theta d theta so that I can integrate that and get a nice thing. So that's going to be my call here, is because secant squared's antiderivative is something I can do. That's what I'm going to do. So if I've pulled out secant squared d theta, what's left in the integral? The other single secant of theta. And its derivative is something we can certainly do. It is secant theta, tangent theta. Didn't leave myself enough room here. D theta. Okay, so that means that this integral, I'll just make it equals down here. So that kind of tenuous here. Okay, that integral is therefore equal to uv. So u is secant theta, v is tangent theta. So we're doing integration by parts, just to remind you. uv minus the integral of v du. I'll have tangent theta multiplied by secant theta tangent theta, which is secant theta. Tangent theta's going to be squared because there are two of them. Tangent times tangent. D theta. And what we're supposed to do in that situation is replace the tangent squared with secant squared theta minus 1. Okay. And that's equal to secant of theta, tangent of theta, minus the integral of secant cubed theta minus secant of theta d theta, which is equal to secant of theta tangent of theta minus the integral of secant cubed theta d theta. And here, please make sure you distribute that subtraction carefully. Minus negative sine theta becomes plus secant theta d theta. Well, This is one of those kind of circular ones. I'm going to see if I left myself enough room over here. This is what we started with, was the integral of secant cubed theta d theta. And that's contained within my answer. So if I add a single secant cubed theta d theta to both sides, I'll have two of them on the left. Equals the secant theta, tangent theta. And I still have the secant of theta over here. And I'm going to go ahead and integrate the secant of theta. That was that formula that I tried to get you to make sure you remember. That's the natural log of the absolute value of secant of theta plus tangent of theta plus C1. Now to solve for the integral we're trying to find the value of, we're going to multiply both sides of the equation by 1/2. And in doing so, I am going to distribute the 1/2 to all terms. So multiplying each term by 1/2, writing down, copying down everything else. And then half of a constant is just another constant. So half of C1 makes that C. So there's our answer for the integral of secant cubed theta d theta. All right, now that we have that, we can take that back to our problem. Remember, a limit as side work that allows you to go off and do other things and come back with an answer. I'm going to need to move over here because that's so long. So the integral of secant cubed theta d theta is, copying down from what we had down there, 1/2 secant theta tangent theta. Okay, let's make sure that's what we have down here. Yep. Plus 1/2 of the natural logarithm of secant theta plus tangent theta minus, and I'm going to hold off on the C because I still have the minus integral of secant theta right above to do, and that is 1/2, no, I'm sorry, it's natural log of the absolute value of secant theta plus tangent theta, and then plus C. All right, so we do have a like term. That natural logarithm expression is identical. So that simplifies to be 1/2 secant theta tangent theta and then 1/2 of those minus one of those makes minus 1/2 of those being the natural logarithm expression. And boy, doesn't it feel like we've done a whole lot. And we're not done yet, because we still have to rewrite this in terms of the original variable x. Woo! Boy, this one's fun and complicated. All right, so I'm going to go back to the expression that I had that related x to theta, which is this one. And I'm going to think of that as secant of theta is x minus 1 over 1. So if this is theta, this is a right triangle, secant of theta is hypotenuse over adjacent. So this is hypotenuse, and this is adjacent. And I know that leg squared plus leg squared equals the square of the hypotenuse. And so 1 plus question mark squared equals x squared minus 2x plus 1. Then if I subtract 1 from both sides, I'll get x squared minus 2x is what question mark squared is equal to. So question mark is the square root of x squared minus 2x. So this is the square root of x squared minus 2x. All right, so doing substitutions. Of course, secant of theta, we knew that from the outset. That was x minus 1. So I didn't need to draw the triangle for this part of it. The secant of theta is x minus 1. That's the original substitution we did. Tangent is opposite over adjacent, and that radical over 1 is going to be that radical. Minus 1/2 natural logarithm of the absolute value of secant theta, which is x minus 1, plus tangent theta, which is that radical over 1 again, so that radical, plus c. This is something you might think of as the super problem, because it involved just about everything we've talked about in this, not everything of course, but a lot of things. This one problem incorporated a bunch of stuff. So I would never put something quite this difficult on the test, I promise you. But it is a good problem in that you realize how much review you need to do, because all of the things I mentioned as we went through are things that you should have known at this point. So let's hope that every one of those things was something you understood. And wow, what a problem. Yowza. That was fun. Okay, so let's move on to trigonometric substitution. For theorem 8.2, this is kind of an introduction to something we're going to be doing in another section or so, which is using special integration formulas that are going to be in a table. And instead of going through the process like we just did, we will rely on the fact that someone has already done that for us and just use those as formulas. And we won't memorize those formulas. Like theorem 8.2, I do not want you to memorize those. What I want you to be able to do is identify which one of those three situations we have, figure out what U is, figure out what A is, figure out what DU is. And once you have all of that, then substitute into the formula on the right side for each U and A with the appropriate value. So, and there's a whole section where that's the main focus, is learning how to integrate with tables. So this is your introduction to that. And again, these are not to be memorized, so kind of hold them so you can see them. And let's do example 3. We're to find the arc length of the graph of f of x equals 1/2 x squared from x equals 0 to x equals 1. And there's a picture provided there. I'm going to sort of draw that without a lot of worry about perfection. It's going to look something like this. And since we're going from 0 to 1, I'm going to stop this at 1. And of course, 1/2 times 1 squared is 1/2. So that point is at 1/1/2. And of course, the origin is the first point. And we're finding the arc length of that. So, speaking of reviewing things that you already know, this is something you're supposed to know how to do still, is the arc length. So the arc length formula for functions demands that we know what the derivative of our function is. Of course, that's just x. And so the arc length formula says that we'll take the integral from a to b, which in this problem is 0 to 1, oops, of the square root of 1 plus the square of our first derivative answer. Our first derivative was x, and that'll be squared dx. You may notice that this one fits the bill of being one of those that we could do because it is in the form a squared. Oops, I started right a squared plus u squared. Come on, erase. There we go. So there we go. So our a squared is 1, which means a is 1. Our u squared is x squared, which means our u is x. And then we're going to substitute for u with a tangent theta so 1 tangent theta. Oh wait, hold on. We could go through all that, but why did I not use theorem 8.2? That was kind of my focus here. We could continue and do that way, but let's just kind of stop that. Stop that presses here. Just kind of don't go there. Let's instead use theorem 8.2 and notice that we have the square root of, well, it's u squared plus a squared is the formula. Okay, well, I didn't need to erase all that. Oh well, that's okay. So let me do it as if I were, pretend like I'm not going to do the trig substitution idea, but use this theorem instead. So I'm going to pretend like I didn't already write all this. So u squared would be x squared. A squared is 1. So u is x. And so du is 1 dx, which we have, so we're ready to go. So this is going to be, according to number 3 in that theorem 8.2, this will be 1/2 times the quantity of u, which is x. Notice I'm not really even going to u here. I'm just using that as a formulation, times the square root of u squared, so x squared, plus a squared, so plus 1, plus a squared, 1 squared is 1, so I'm not going to write that, times ln of the absolute value of u, which is x, plus the square root of u squared, which is x squared, plus a squared, which is 1. Close off the absolute value, close off the parentheses, and evaluate that from 0 to 1. So we'll substitute in for x, first with 1, so this will be 1 times the square root of 2, so square root of 2, plus the ln of 1 plus the square root of 2. And I know that square root of 2 and 1 are both positive, so their sum must be positive, and I don't really need the absolute value anymore. Minus 1/2. 0 times 0 squared plus 1 is 1, so 0 times 1 is 0, plus the natural logarithm of 0 plus 0 squared plus 1 is 1, square root of 1 is 1, 0 plus 1 is 1. And the natural log of 1 is 0, so that whole back part is 0. So we get square root of 2 over 2 plus 1/2 the natural logarithm of 1 plus square root of 2 as our final answer. Okay. Okay, that ends this section. I will see you in class.